Greetings of day to all of you. In our last lecture, we started discussions on analysis of various types of PWM techniques from the point of view of distortion in the voltages and distortion in the currents. And we came up with some very important, conclusions. We found that, for low modulation indices, conventional space vector based PWM technique is suitable because it results in less harmonic distortion, and for high modulation indices, advanced bus clamping PWM techniques are suitable as they result in less harmonic distortion. Okay, right. Now, in today's lecture, we are going to discuss about how to calculate RMS line current ripple from the notion of stator flux ripple. Okay, the topic of today's discussion is analysis of RMS line current ripple, RMS line current ripple from the notion of stator flux ripple. Stator flux ripple. What we will do, we will first of all find error voltage vector, because it is the error voltage vector which results in distortion in inverter output voltage. And this error voltage vector is responsible for, ripple in the current. When I say ripple in the current, it exclusively means the harmonic distortion of the current. Okay, so to begin with, let us review some of the equations which we have discussed in the last lecture. First is that nth harmonic component of current In is equal to Vn by n omega L, where omega is equal to 2 pi f1. F1 is the fundamental frequency, and L is equal to stator inductance plus rotor inductance of induction motor. So we have already got this equation in last class. This means nth harmonic component of current is proportional to nth harmonic component of voltage divided by order of harmonic. So higher the order of harmonic, smaller will be the nth order harmonic of current. This was one equation that we got in last class. Simultaneously, the second very important this parameter that we wrote was weighted THD. Weighted THD of voltage. If you remember, it was defined as under root of square of Vn by n, under root of summation of Vn by n square divided by V1. Okay, and we already know that this Vn by n is proportional. I mean, it represents the nth harmonic component of current. So in a way, this weighted THD of the voltage gives us information about the distortion in the current, or it gives us information about how much is the THD or distortion level in the current at a particular harmonic voltage. Okay, we also have defined this term, that is THD in the current equal to under root of summation In square by I1, where n is not equal to 1, because n equal to 1 is fundamental component. So n is basically all types of harmonics, maybe fifth harmonic, seventh harmonic. In fact, if you are using PWM technique, then there will not be these lower order harmonics, 5th, 7th, 11th, 13th. Then the most predominant harmonic is at switching frequency or carrier frequency Fc and its first sideband. Then sideband around 2 Fc. Then 3 Fc and its sideband, and so on. But we are mostly interested with first two sidebands, because the higher sidebands are quite insignificant to be considered. right? Now this THD of the current can also be written as, now if you find the RMS value of all these components of current, for example, you find RMS value of these RMS value of harmonic currents, and maybe, for example, we can start with n equal to 37, n equal to say 49, higher, of course, higher values of n harmonic order depending upon the switching frequency, and you add up all those harmonic components, take square, do the square of them, and take square root of that will give us nothing but RMS value of the current, ripple current, that is called IRMS tilde. This means a ripple current divided by I1. So this under root of summation IN square is nothing but RMS value of all harmonic currents, and we call RMS value of all harmonic currents which are present in the windings of the stator winding of induction motor, we call RMS value of, we call the sum of RMS value of all the harmonic currents, we call them this RMS, this ripple current. So what is this IRMS tilde? It is nothing but, it's called a ripple current. So what is this ripple current equal to? It is the RMS value of all the harmonic currents which are flowing in the induction motor winding. So now our job, primary job, is to find this ripple current. If we are able to find RMS value of ripple current, we'll be able to find distortion level of current which is flowing in the stator winding of induction motor. Now, from frequency domain point of view, how can you find this RMS value of ripple current? By using this equation. So put different values of n here. Say, n is the harmonic order. So n may be, for example, x, and maybe y, and maybe z. So for different values of these harmonic orders, find summation of this. That will give you RMS value of ripple current. Divide that by I1, that will give you THD in the current. But it will be a bit difficult to find, the RMS value of current that way, because in frequency domain, you have to first of all find what is the magnitude of current, harmonic current at a particular harmonic order. Say at n equal to x, you have to first of all calculate Ix. Then at n equal to y, you have to find Iy. Then at n equal to z, you have to find Iz, and so on. And then you have to find, this IN square, sum of squares of those, and take square root of that. It becomes a little difficult, little inconvenient. So it has been therefore found that instead of working in frequency domain to find the RMS value of ripple current, it is very convenient, very easy to find RMS value of ripple current if you work in time domain or space vector domain. So what we will do now, we will find the RMS value of this ripple current, IRMS tilde, in time domain or space vector domain. Space vector domain, not in frequency domain, because in frequency domain you have to find for different harmonic orders, you have to find magnitudes of harmonic currents, you have to take square of them, you have to then add them and find square root of, and that will give you RMS value of a ripple current. But it will be very convenient to find RMS value of ripple current, which will actually represent the distortion level in the motor winding current, if you find RMS value of ripple current in time domain or space vector domain. Now the question is how to find it in space vector domain. Let us take conventional space vector PWM. Conventional SVPWM technique. With conventional space vector PWM technique, we know that in sector 1, if we consider sector 1, the switching sequence is like this. Switching sequence is 0, 1, 2, 7, then 7, 2, 1, 0. That means for time interval T0, which is equal to Tz by 2, null vector 0 with switching sequence minus 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 is applied. Then for time interval t1, active vector 1 with switching sequence plus minus minus is applied. Then for time interval t2, active vector 2 with switching sequence plus plus minus is applied. Then for another null vector t7, which is also equal to tz by 2, null vector 7 with switching sequence plus 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 is applied. This is what happens in one subcycle, ts. And then in another subcycle, the same vectors are applied but in reverse order. Here it is 0, 1, 2, 7. Null vector 0 is applied for time tz by 2. Active vector 1 is applied for time t1. Active vector 2 is applied for time t2. And null vector 7 is again applied for time tz by 2 in one subcycle. And in the subsequent subcycle, these vectors are applied in the reverse order. That means first null vector 7 will be applied for time interval tz by 2. Then active vector 2 will be applied for time interval t2. Then active vector 1 for time interval t1. And then finally null vector 0 for time interval tz by 2. Okay. So that will synthesize a reference vector, right? Now, the question is, when we apply these, null and active vectors, say for in sector 1 and sample, them. In each sample, we are basically synthesizing a rotating reference vector, vref, okay? And this rotating reference vector is rotating along a circular path in counterclockwise direction, and it becomes our, reference signal. And from this reference signal, switching sequences are generated as per this switching sequence, say in sector 1. And once once time calculations are done, and for what time interval t1 vector 1 has to be applied, for what time interval vector 2 has to be applied, and so on, these switching sequences are applied, or switching pulses which are stored in a lookup table. They are fetched from there and applied to the devices or switches of inverter, and that will produce three-phase PWM voltage waveforms whose instantaneous average values will be sinusoidally varying. Three-phase line-to-line voltages and three-phase phase to neutral voltages or phase voltages. We already know that about that. Now, when this reference vector is synthesized, actually, this is the reference vector, desired reference vector, which we want to apply across the load. Basically, this reference vector, it represents a set of three-phase voltages. And when we apply this reference vector across the load, which may be an induction motor, sinusoidally varying voltages are applied across the motor terminals. But actually what happens, this is what is desired. What you are applying is slightly different from what is desired when you apply different switching sequences. And as a result of difference between what is desired and what is actually applied across the motor terminals, an error occurs between what is desired and what is actually applied. And that error is called error voltage vector. And it is because of this error voltage vector which results in current ripple. See, if applied voltage is exactly equal to V reference, then there would have been no error voltage vector. Then there would have been zero, ripple in the current. And THD of the current which is flowing in the stator winding of induction motor would have been 0. But that is not true. What is actually desired is this, but what we actually apply is different from this. While synthesizing this V reference vector, say in sector 1, this is the switching sequence that we are applying. At any instant of time, what we apply is different from what is desired. Okay? And that results in error voltage vector, and that error voltage vector is responsible for current ripple. Okay? So error voltage vector gives rise to current ripple and hence harmonic distortion of motor currents. Let us see how to calculate that harmonic distortion or how to calculate that current ripple. For that purpose, we'll take space vector diagram in sector 1. For example, this is our vector 1. This is null vector 0, minus, 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 right? And this is vector 2. This is vector 2 with switching sequence plus plus minus. This is null vector 0 with switching sequence minus minus minus. And this is the desired rotating reference vector. This is vref, desired rotating reference vector. This is active vector 1 with switching sequence plus minus minus. Right? Now, let us call this angle as theta s. What we do, how do we synthesize this reference vector? By applying null vector 0 for time tz by 2, active vector 1 for time t1, active vector 2 for time t2, then null vector 7 for time tz by 2 again in one subcycle, and in reverse order in another subcycle. We already know about that. And that will generate, or that will synthesize, this reference vector. Okay. So I will write here. So therefore switching sequences 0, 1, 2, 7 in a subcycle. Let us see what happens when null vector 0 is applied. So when null vector 0 is applied, there will be error voltage vector. Similarly, when active vector 1 or active vector 2 or null vector 7 is applied, there is always an error voltage vector. Error between what is desired and what is actually applied. So I will write here error voltage vector when null vector 0, which is a switching sequence of minus minus minus, is applied. How do we generate, or how do we synthesize this vref? By applying these vectors, okay, in a particular subcycle in the sequence 0, 1, 2, 7, and in next subcycle in reverse order 7 to 1, 0. So what happens when, so we start with applying of null vector 0. This null vector 0 is applied for time interval tz by 2, t naught, which is equal to tz by 2. When this null vector is applied, so we are applying this null vector. Okay. So what we are applying is this null vector. What is the length of null vector? Null vector has 0 length. And what is desired? So it is very interesting to see what is desired is vref. And what we are applying is null vector 0. So therefore there is an error between what is desired and what we are applying. This is what is desired, vref. But what are we applying? We are applying 0. So this red line shows error vector. So this shows V error. This is the error voltage vector. Because what we are desiring is vref, but what we are applying is 0, which has 0 length. So what is the error between this and this? This is the error between what is desired and what is actually applied at any instant of time, right? So therefore, V error voltage vector is equal to minus vref. It is minus vref. Okay. Now, since we are working in alpha and beta axis, say for example, this is alpha. We are working in alpha beta, this stationary reference frame. This is alpha axis, this is beta axis. Let us try to find out, resolve this error vector into alpha component and beta component, right? So if you find error voltage vector V alpha tilde, whenever I will put this symbol tilde, it means error. So V alpha tilde, it is actually applied vector, applied voltage vector minus reference voltage vector along alpha axis. Similarly, if I write V beta tilde, that is also applied voltage vector or applied vector minus what is actually desired or reference vector along beta axis. Okay, so therefore if I find V alpha, so V alpha, therefore V alpha is equal to what is along alpha axis, what are we applying? And we are applying 0 voltage vector. Okay, 0 voltage vector has a length of 0, so it is 0 minus Now this is our Vref. What is the component of this Vref along alpha axis? So that will be reference vector along alpha axis. Reference vector is at an angle of theta s. It is somewhere here. And what is its component along alpha axis? If you find, so base by hypotenuse is cos theta. So its component along alpha axis is Vref cos theta s. So therefore, the error voltage vector along alpha axis is 0 minus Vref cos theta s. So it is minus Vref cos theta s. Fine. So therefore, we have been able to find error voltage vector, the component of error voltage vector along alpha axis. In a similar way, we can find the component of error voltage vector along beta axis. That is beta component of error voltage vector. So V beta is equal to applied voltage vector. Applied voltage vector is 0. Since 0 has 0 amplitude, it has 0 length, so it is again 0 minus a reference vector component along beta axis. The reference vector component, just few moments back, we found reference vector component along alpha axis is Vref cos theta s, and its component along beta axis will be Vref sin theta s. It's very much clear. So therefore, V beta tilde, that is equal to minus Vref sin theta s. So therefore, we found that when null vector 0 is applied for time interval t0, which is equal to tz by 2, it results in difference between what is desired and what we actually apply, and that gives us error voltage vector. And that error voltage vector has the component of error voltage vector along alpha axis is minus Vref cos theta s, and the component of that error voltage vector along beta axis is minus Vref sin theta s. Fine, I hope this is clear. Now very quickly, now we'll try to find out error voltage vector when active vector 1 is applied, because I again write here, this is the sequence 0, 1, 2, 7 in a subcycle. We have found error voltage vector when null vector 0 is applied. We have found its alpha component as well as beta component. V alpha tilde is equal to minus Vref cos theta s, and V beta tilde is equal to minus Vref sin theta s. After this, after tz by 2 time, for time interval t1, active vector 1 is applied. Now when active vector 1 is applied, there will be again an error between what is actually desired and what we actually apply, and that will give rise to error voltage vector again. So I will write here error voltage vector when active vector 1, which has a switching sequence plus minus minus, is applied. Let us try to find out this error voltage vector. So this is again our alpha axis, and this is beta axis. Along this I have this is 0 or null voltage vector 0 minus minus minus. V1 will be along alpha axis and V2 will be somewhere here. This is V2 or 2. It's switching sequence plus plus minus. And this is our Vref. Fine. Let us suppose we apply vector 1, active vector 1. Now when active vector 1 is applied, it's applied, the active vector 1 is along alpha axis. Okay. What is desired? Desired is Vref. But what are we applying? We are applying 1. Vref vector, again, this angle is theta s. Now we can very clearly see Vref vector is what should have been actually applied across motor terminals. But for time interval t1, what are we actually applying? We are not applying Vref, we are applying 1 for time interval t1. So therefore, between this and this, there is an error. So this is that error, voltage error, V error. Okay. So this is the error between what is actually desired and what we actually apply for time interval t1. So this is very interesting, you can see. So therefore, V alpha tilde, that is error voltage. This is the error voltage vector. Its alpha axis component will be is equal to applied, what we are applying, minus what is the reference vector. What are we applying across along this alpha axis? We are applying active vector 1, whose switching sequence is plus minus minus, and we already know that the length of this vector is VDC. We have found it in one of the early classes. Then when these space voltage vectors 1, 2, 3, 4, 5, 6 are applied, their length is VDC. So therefore, what is actually applied along x-axis, what is actually applied along alpha axis is this active vector 1, whose length is VDC. So I will write here VDC minus what is desired, Vref. And what is the component of Vref along alpha axis? So again, if you find that, that is Vref's cos theta s. Just few moments back we have found the component of Vref along alpha axis is Vref cos theta s. So therefore, this is the component of error voltage vector along alpha axis. In a similar way, we can find the component of error voltage vector along beta axis. So what will be the component of error voltage vector along beta axis? V beta tilde. That is again equal to what is actually applied minus what is the reference vector component along beta axis. What is actually applied is 1, but that is applied along alpha axis. What is its component along beta axis? Since alpha and beta are at 90 degrees, so cos 90 degrees is 0. So this applied voltage vector has no component along beta axis, 0 minus. What is the reference voltage vector component along beta axis? That is Vref sine theta s. So therefore, error voltage vector along beta axis will be minus Vref sine theta s. Fine. So when active vector 1 is applied for time interval t1, it also results in error between what voltage vector we actually desire and what we actually apply. And the alpha component of that error voltage vector along alpha axis is VDC minus Vref cos theta s, and error voltage vector along beta axis is minus Vref sine theta s. Fine. Now after this, we will discuss we will try to compute the error voltage vector when active vector 2 is applied. So I will write here now error voltage vector when active vector 2, which has a switching sequence of plus plus minus, is applied. When active vector 2 is applied, and we know that active vector 2 is applied for a time interval t2. Okay, let us draw the space vector diagram for sector 1 again. This is again our alpha axis, this is beta axis. Okay, this is our, we are applying active vector 1, this is null vector 0, this is active vector 2, and this is our reference vector. Say for example, this is reference vector. At an angle of theta s. Right? Now we can very interestingly see that again our desired vector, voltage vector, which should have been applied across the induction motor winding is Vref. But what are we applying? We are applying 2. So this gives error between what is desired and what we apply. This is V error voltage vector. Now again, this error voltage vector we can resolve into alpha component and beta component, and its alpha component V alpha tilde is equal to alpha component. So what is applied across alpha axis? See, actually we are applying vector 2. Now this is vector 1, this is vector 2, और ये आपका sector 1 है. इस sector 1 में this vector 2 and vector 1 are 60 degrees apart from each other. We already know that in sector 1 we are applying null vector 0, active vector 1, active vector 2 and null vector 7. Now as far as active vector 1 and active vector 2 are concerned, they are at 60 degrees. So therefore, what is actually applied along alpha axis is the component of this active vector along alpha axis, and that is, what is the length of this active vector? इसकी भी length VDC है, that is VDC at an angle of 60 degrees. See, this is VDC, okay? Along 2 it is VDC, and along 1 it is VDC at an angle of, its component along alpha axis is VDC at an angle of 60 degrees, right? Minus, what is the reference vector component along this axis, alpha axis? It is Vref at an angle of theta s. The component of active vector 2 along alpha axis is VDC at an angle of 60 degrees, and the component of Vref along alpha axis is Vref at an angle of theta s. So V alpha therefore will be VDC cos 60 degrees. It's VDC by 2 minus, this will be Vref cos theta s. So this is the component of error voltage vector along alpha axis when active vector 2 is applied. In a similar way, we can find the component of error voltage vector along beta axis when active vector 2 is applied. So you can find that V beta will be equal to root 3 by 2 VDC minus Vref's component along beta axis is Vref sine theta s. Fine. So that is it. So therefore we have applied first null vector 0, and we have found the error voltage vector and resolved that error voltage vector into alpha component and beta component. And then when we applied active vector 1, we found the error voltage vector and its components along alpha and beta axis. And now when we apply active vector 2, we find that this is the error voltage vector. This is the error between what is actually desired and what we actually apply. And we resolve this error voltage vector in its alpha components and beta components, and these are its alpha and beta components. Like error voltage vector along alpha axis is VDC by 2 minus Vref cos theta s, and error voltage vector along beta axis is root 3 by 2 VDC minus Vref sine theta s. That's it. This is for one sector, sector 1. You can repeat it for other sectors. You can repeat this exercise for sector 2, sector 3, 4, 5 and 6. So in that way you will be able to find error voltage vectors and their alpha and beta components. But there is one drawback of this technique. The drawback is that when you move from one sector to another sector, the values of these the error voltage vectors, they are different. V alpha and V beta tilde, they keep on changing in different sectors. So V alpha tilde and V beta tilde, that means error voltage vector component along alpha axis and error voltage component along beta axis, they keep on changing from sector to sector, sector to sector. Okay, so therefore you have to repeat this exercise in every sector, which becomes cumbersome. Is there any method where we don't want to repeat it in all the sectors, where we find it in just one sector and find the values which are not changing in other sectors? Yes, we can do that. If instead of working in alpha beta reference frame, we work in DQ reference frame. So I'm going to discuss that with you. See, we have discussed that if we have a three-phase stationary reference frame, say ABC reference frame, ABC, we transform it into stationary reference frame, alpha beta reference frame. In fact, when we studied our space vector pulse width modulation, this is what we did in the very first class. We transformed from stationary ABC reference frame to stationary alpha beta reference frame. Now what we will do, in order to find the error voltage vector in a more convenient way, we will transform our frame from stationary alpha beta reference frame to synchronously rotating reference frame DQ. See, alpha beta reference frame is stationary reference frame. stationary reference frame. It has two components, one along alpha and another along beta. They are 90 degrees apart, but those quantities are stationary. On the other hand, DQ reference frame is a synchronously rotating reference frame. It is a synchronously rotating or revolving reference frame. Here what we do, we have two quantities, D component and Q component. They are not stationary. They are continuously rotating in the counterclockwise direction, just like your space vector is rotating, reference vector is rotating. So what we will do, we will transform from alpha beta stationary reference frame to DQ synchronously rotating reference frame, and we will try to calculate these error voltage vectors in this DQ rotating reference frame. And in DQ rotating reference frame, it will be very convenient for us to work with these error voltage vectors rather than working in stationary alpha beta reference frame. Now the question is how to transform from alpha beta reference frame to DQ reference frame. I'm not going into very much details. I'm sure that you must have studied the transformation from one reference frame to another reference frame in details in your advanced electric drives. How to transform from stationary alpha beta reference frame to synchronously rotating DQ reference frame. You must have studied that in advanced electric drives course. Okay, so I will just give an overview of that. Stationary alpha beta to synchronously revolving or synchronously rotating DQ reference frame. DQ reference frame. So when we work on our space vector domain is basically an alpha beta reference frame. So what we will do, we will transform from stationary alpha beta reference frame to synchronously rotating DQ reference frame. So this is how transformation is to be done. For example, this is alpha axis and this is beta axis. What we are doing, we are transforming this alpha beta into DQ. For example, this is D axis and this is Q axis. D axis and Q axis are at 90 degrees with respect to each other, and both the axes are rotating in anti-clockwise direction or counterclockwise direction at a speed omega. Okay, so this is rotating reference frame. Alpha beta reference frame is stationary reference frame. DQ reference frame is rotating reference frame. Let us suppose this angle is phi, this angle is also phi. So now you have to find alpha, V alpha and V beta in terms of VD and VQ. For example, if you find V alpha in terms of VD and VQ, now you have to find VD and, since you are transforming from alpha beta reference frame to synchronously rotating DQ reference frame. Earlier you were working in alpha beta reference frame and you have two voltage vectors, V alpha and V beta. Now you will work in synchronously rotating DQ reference frame. Here you have two voltage vectors, VD and VQ. So VD and VQ in terms of V alpha and V beta will be like this. For example, VD will be equal to V alpha cos phi plus V beta cos of 90 degrees minus phi. Okay, so you have to find the component of alpha along D axis, and that will be cos phi, V alpha cos phi, and beta component along alpha axis, along D axis will be V beta cos of 90 degrees minus phi, because this is 90 degrees, this is phi, and this is 90 degrees minus phi. In a similar way, if you find VQ component, first of all, let me complete this. So this is VD equal to V alpha cos phi plus V beta. What is cos 90 degrees minus phi? That is sin phi. This is equation number 1. Similarly, you can find Q component, VQ, in terms of alpha and beta. When you transform alpha and beta into D and into Q, so you will find VQ is equal to minus V alpha sine phi plus V beta cos phi. This is the component of alpha along, q-axis. So you can find component of this alpha along q-axis and component of beta along q-axis. Component of alpha along q-axis is minus V alpha sine phi, and beta component along q-axis is V beta cos phi. I am not going into details. I suppose that you already know this transformation. So therefore we have two equations. We have equation for Vd, we have equation for Vq. So this is how mathematical transformation is done from alpha beta reference frame to synchronously rotating dq reference frame. So we can put these equations in matrix form. So I can write in matrix form. I will have now Vd Vq equal to a matrix into V alpha V beta. What is this matrix? The V alpha, here it is cos phi, and here it is sine phi, and here it is minus sine phi, here it is again cos phi. This is the matrix. So Vd is equal to V alpha cos phi plus V beta sine phi. That's equation 1. And Vq is equal to minus V alpha sine phi plus V beta cos phi. That corresponds to equation 2. So this is how transformation is done from stationary alpha beta reference frame to synchronously rotating dq reference frame. So with this background, let us try to now find out error voltages in dq reference frame rather than in alpha beta reference frame. Okay, fine. So we'll now try to find out error voltage vector when null vector 0 with switching sequence minus 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 is applied. We have already done it for alpha beta reference frame. Now we will try to find out this error voltage vector in dq reference frame. Now fine, this is our, for example, alpha axis, and we already know that this is our beta axis, right? And say for example, we are applying active vector 1 plus minus minus, and we are applying active vector 2 plus plus minus, and then this is null vector, for example, minus minus minus, and this is our reference vector Vref. I should write it here, Vref. It is at an angle of theta s with respect to alpha. Now we don't need to find error vector in alpha beta reference frame. We have to transform from alpha beta reference frame to dq reference frame. So what I will do, along Vref, I will have an axis called q axis. Q axis I will put in straight line along Vref axis. Along Vref I will have q axis, and at 90 degrees to this I will have d axis. So this is d axis, d, and this angle is 90 degrees. So this is my q axis, this is my d axis. So therefore my, what am I applying? What is desired? Vref. What am I applying? I am applying null vector 0. So this is my error. This is error voltage vector, V error. This red line shows error voltage vector, because what is desired is Vf, but what I am applying is 0. So this minus this is the error between the two voltage vectors. Now I will try to find out component of this error voltage vector along d axis and along q axis. So component of this voltage vector along q axis, Vq tilde, is equal to what is actually applied. What is applied along q axis? The q axis, along q axis we are applying 0 voltage vector, 0, whose length is 0, minus what is actually desired. What is actually desired? Vref. Since Vref is along q axis itself, so it does not have, its angle is 0, so it is Vref. So therefore it is equal to minus Vref. This is the component of, error voltage vector along q axis. What is the component of this error voltage vector along d axis? Along d axis Vd tilde is equal to error voltage vector along d-axis, that's again 0, minus reference voltage vector along d-axis. You can see this reference voltage vector is along q-axis and d-axis. They are at 90 degrees with respect to each other. Cos 90 is 0. So there is no reference component of reference voltage vector along d-axis. So 0 minus 0 is 0. So therefore, we have found the error voltage vector. And error voltage vector is VR when null vector 0 is applied. And this VR we have divided into or resolved into two components, one along q-axis, another along d-axis. So along q-axis, the component of this error voltage vector we have just now found, it is minus Vref, and the component of error voltage vector along d-axis is 0. So this is it. Okay. Now let us apply active vector 1 and find the error voltage vector again. So now I will write here error voltage vector when active vector 1 is applied. So let us draw the diagram, space vector diagram again, and we'll try to find out error voltage vector in DQ reference frame. Now again, this is our alpha axis and this is beta axis. Okay, so this is null vector, minus, minus, minus. We are applying active vector 1 along alpha axis. We are applying active vector 2. This is active vector 2. Okay, and our reference vector is somewhere here. This is our reference vector, Vref. It's at an angle of theta s. And यही हमारी q axis है. This is our q axis. This is q axis, right? So let us suppose this is active vector 1. So we are applying null vector 0, we are applying active vector 1, we are applying active vector 2, and that gives rise to our desired reference vector is Vref. That's here. That's along q axis. और ये हमारी d axis है. This is d axis. Q axis and d axis are at 90 degrees with respect to each other. Now fine. What is desired is Vref. What we are actually applying for time interval t1 is 1. So therefore between this and this there is an error. Or wo error ye hai. So this is my voltage error. This is my error voltage vector, VR. So this error voltage vector between desired voltage and actual voltage vector, I will now resolve into Q component and D component. Therefore, error voltage vector along Q axis or Q axis component of error voltage vector will be equal to what is actually applied along Q axis. What is actually applied along Q axis? See, along this alpha axis, we are applying active vector 1, whose length is VDC. इसका component अगर आप along Q axis निकालोगे, if you find its component along Q axis, see, this is along alpha axis. Along Q axis, the angle is theta. If you find active vector 1 component along Q axis, that will be VDC cos theta s. Simple. VDC cos theta s minus the desired vector. What is desired vector along? Desired vector is Vref, and since that is along Q axis itself, so it is Vref. So it is therefore VDC cos theta s minus Vref. So this is the error voltage vector component along Q axis. So in a similar way, what is the error voltage vector along D axis? ये मेरी D axis है. ये error voltage vector है. Error voltage vector का component, if it's this is my vector 1. What is actually applied is vector 1, and what is desired is Vref. Okay. So active vector 1's component along Q axis was VDC cos theta s, and what is active vector 1's component along D axis? That will be VDC sin theta s. Simple. Minus what is the component of this Vref along D axis? Now you can see this Vref and Q axis are aligned, and D axis is at 90 degrees to Q axis. That means D axis and V ref are at 90 degrees. So cos 90 degrees is 0, so it is minus 0. So therefore VD tilde is VDC sine theta s. So therefore error voltage vector along Q axis, or the component of error voltage vector along Q axis, is VDC cos theta s minus V ref, and the component of error voltage vector along D axis is VDC sine theta s itself. Fine. When active vector 1 is applied. Now let us try to find out error voltage vector when active vector 2 is applied. So I will write here error voltage vector when active vector 2 is applied. When 2 is applied. Let us try to find out. So let us draw the space vector diagram again. So this is again our alpha axis. This is alpha axis and this is beta axis. This is active vector. This is null vector. For example, this is 0. This is active vector 1. And we are applying active vector 2. This is 2 plus plus minus. And our reference vector is somewhere here. Say for example, our reference vector is somewhere here. This is reference vector Vref. Should write it like this, Vref. And it is aligned along Q axis. And where is our D axis? This is D axis at 90 degrees and this is minus D. Anyway, and this angle is theta s. So what are we applying? We are applying active vector 2. So that is what is applied. But what is actually desired? Vref. So therefore, this is the error between what is actually applied and what is desired. V2 minus Vref is the error, and that is called error voltage vector VR. Now we will try to resolve this error voltage vector into Q component and D component. So Q component of the error voltage vector is, see, its Q component is, see, we are applying error voltage vector 2, okay? That's along this axis. Its component along Q axis is VDC cos of 60 degrees minus theta s. Because what is this total angle? This total angle is 60 degrees. 60 degrees में से अगर आप theta s निकालेंगे, वो ये angle है. That's cos of 60 degrees minus theta. So the component of this active vector 2, whose length is equal to VDC along Q axis, is VDC cos of this angle, and this angle is 60 minus theta s. That's what I have written. Minus desired vector. What is desired vector? Desired vector along Q axis is Vref. Vref itself. So therefore, this is the Q component of error voltage vector when active vector 2 is applied. What is the D component of error voltage vector? D component of error voltage vector is see, this is 2. 2 is applied here. Its component along Q axis was VDC cos of 60 degrees minus theta, and along D axis, अगर इसका component along D axis यहाँ आप निकालेंगे, it will be minus VDC sine of 60 degrees minus theta s minus the component of reference vector along D axis. Now the D axis and this reference vector, this is minus D axis, this is Q axis, which is along reference vector. It's 90 degrees, cos 90 degrees is 0. So therefore, D component of error voltage vector when active vector 2 is applied is simply minus VDC sine of 60 degrees minus theta s. That's it. So therefore, in sector 1, we have applied null vector 0 first, and we found error voltage vector and we resolved it into D component and Q component. Then when active vector 1 was applied, we again found the error voltage vector and resolved that into D and Q components. And finally, when active vector 2 is applied, we found that this is the error voltage vector and we again resolved it into Q component and D component. For example, VQ tilde is VDC cos of 60 degrees minus theta s minus Vref, and Vd tilde is minus Vdc sine of 60 degrees minus theta s. That's it. So this is how it is done. Okay. Now, once you have found error voltage vectors, for example, for a particular switching sequence 0, 1, 2, 7, in sector 1, you have found what is the error voltage vector when null vector 0 is applied. What is the error voltage vector when active vector 1 is applied? Similarly, what is the error voltage vector when active vector 2 is applied? And you have resolved them into D and Q components. We have done it. Okay. Once this is done, once you know error voltage vector, then if you integrate the error voltage vector, that will give you stator flux. Because by definition, when you integrate a voltage vector, that gives the flux, stator flux. Okay. So therefore, we will try to now find out the stator flux vector. I will write here stator flux vector. How do you find the stator flux vector? By integrating error voltage vector. Integrating error voltage vectors. Error voltage vectors. Okay. So let me try to explain it with the help of diagram. This is our alpha axis. For example, this is our alpha axis and this is beta axis, right? Now this is null vector 0 and of course 7 also. Active vector 1 is applied along alpha axis. This is my active vector 2 plus plus minus. Let me write it. This is active vector 2 plus plus minus. And this is my reference vector. This is Vref at an angle of theta s. Now this Vref is along Q axis. If you extend it, it will be your Q axis. And where is your D axis? Your D axis is somewhere here. This is D axis and Q axis and D axis are 90 degrees apart with respect to each other. Now when you apply null vector 0, this is the error voltage vector. उस वक्त ये error voltage vector है. When you apply active vector 1, for example, it's switching sequence plus minus minus. At that time, this is the error voltage vector, VR. When you apply active vector 2, for example, you apply active vector 2 plus plus minus. At that time, this is the error voltage vector, VR. Okay. I repeat, when null vector 0 or null vector 7 is applied, the error voltage vector is this. When active vector 1 is applied, this is error voltage vector, VR. And when active vector 2 is applied, this is the error voltage vector, right? So since this is my Q axis, what I will do, this is D axis, I will take this D axis somewhere here for better understanding. So ये मेरी D axis है. Okay. Now, first of all, I am applying null vector 0. I am applying it for time interval Tz by 2. And this is the error voltage vector when I apply null vector 0. This is what is desired, VR, and this is what we are applying, and this is error voltage vector. This is error voltage vector when null vector 0 is applied. And this error voltage vector, when I am integrating it, it will give me flux. It will give me stator flux. Integration of error voltage vector gives stator flux. And this stator flux, therefore, it will be moving in this direction. Like this, it will be moving in this direction. इस direction में move करेगा, and this stator flux, which is actually found by integrating this error voltage vector VR when null vector 0 is applied. Null vector 0 is applied, and at the end of this null vector 0 is applied for a time interval t0, which is equal to Tz by 2. Therefore, my stator flux will be moving. It's constant and it will be moving in this direction. The speed at which it will be moving along this direction, because मेरा null vector is direction में, error vector is direction में, तो इसी direction में when I integrate it, so I will have a error flux vector, and that error flux vector will start moving like this. The speed at which it will move, that will be proportional to magnitude of this error voltage vector. So therefore, when null vector 0 is applied, my stator flux, which is found by integration of this error voltage vector, moves in this direction. That is when for time interval tz by 2. When tz by 2 ends, then active vector 1 is applied. Now we can very interestingly see when active vector 1 is applied. I should show this active vector 1 somewhere here. This is active vector 1 plus minus minus. And this is error voltage vector VR. When active vector 1 is applied, this is my error voltage vector. Now you integrate this error voltage vector. When you integrate this error voltage vector, now you can see when this error voltage vector is integrated. Okay, so I will have the stator flux which will move like this. It will move parallel to this line. ये line है, इसी के parallel ये move करेगा like this. So this is when active vector 1 is applied. So I repeat, when active vector 1 is applied, the error voltage vector is this between reference and actual vector, and when I integrate this, I get a stator flux which moves along this line, and this line is parallel to this error voltage vector. Okay, so this will happen up to this, and at the end of this, what is the time? Here time was tz by 2, here time is tz by 2 plus t1, because this active vector 1 is applied for a time interval t1, so total time interval is tz by 2 plus t1. उसके बाद हम क्या करते हैं? उसके बाद हम active vector 2 apply करते हैं, and when active vector 2 is applied, right? What is the error voltage vector? This is the error voltage vector, and when I integrate this error voltage vector, I will get a stator flux which will move along this line, a line which is parallel to this, error voltage vector. Okay, this is when active vector 2. So my stator flux will move along this line. The speed at which my stator flux will move will be proportional to magnitude of this error voltage vector. Okay, so when error voltage active vector 2 ends, what is the total time interval? It is tz by 2 plus t1 plus t2, because active vector 2 is applied for time interval t2. So total time is tz by 2 plus t1 plus t2. उसके बाद null vector 7 apply करते हैं, and when null vector 7 is applied, my flux, this is 7, stator flux moves back to origin. ये मेरा origin है. So it starts from 0, goes like this and comes back. So therefore this stator flux I can show with the help of this arrow. This is the stator flux error. Stator flux error vector. So I should write here stator flux error vector. This is the stator flux error vector. When null vector 0 is applied, ये यहाँ से शुरू होता है, it moves like this. When active vector 1 is applied and I integrate this error voltage vector, my stator flux error vector moves along this line like this. ये इस line के along move करेगी. And then when active vector 2 is applied, my error vector is this. I integrate this, और मेरा stator flux vector इस तरह move करेगा. And when null vector 7 is applied, it moves back. So this is how my stator flux error vector moves like this. Then it traces this path. When active vector 1 is applied, when active vector 2 is applied, it moves along this. And when active vector 7 is applied, it moves here. So this is how we find stator flux error vector. Okay, the stator flux error vector moves along a triangle like this. And switching sequences, you can see 0, 1, 2, 7. And this is how it moves along this triangle. Okay. So once I know the stator flux error vector, this is my stator flux error vector. I repeat, this arrow, it moves along this triangle like this. When this in a subcycle, my switching sequence is 0, 1, 2, 7. This is how it moves. It traces this triangular path. Now I want to resolve this stator error flux vector into D component and Q component. Let us see how we can do that. So I will very quickly draw it again. ये मेरी Q axis है, this is D axis, this is error vector 0, this is active vector 1, this is active vector 2, and this is null vector 0. Null vector 0, error, active vector 1, active vector 2, and null vector 7. और ये मेरा stator flux error vector है, psi tilde. Okay. Now this psi tilde I want to resolve into D components and D component and Q component. So I can do that very easily. This is time axis and this is psi Q tilde. That means the component of this stator flux error vector along Q axis. It's Q axis component and its D axis component will be here, psi D tilde. Now it is very interesting to see that when null vector is applied, when null vector is applied, what happens to your psi? Psi ये है, it moves along this Q axis. आपकी Q axis positive इस direction में और इस direction में negative है. That means your psi moves in this direction. So therefore what is its Q component? Its Q component is becoming negative. So it starts from 0, ये 0 है, and then it moves in minus Q axis direction like this. So therefore that means when null vector 0 is applied. Okay. So this is time interval Tz by 2. At the end of this time interval Tz by 2, my Q component of stator flux error vector moves in this direction. Okay, this is positive Q axis, but it moves in the negative direction. Say it moves in the negative direction. I'm showing it with respect to time axis. Okay. Once Tz by 2 time interval is over, then active vector 1 is applied. Now you can see when active vector 1 is applied, very interestingly you can see now your flux vector moves in this direction. So here it is most negative and then it becomes less and less negative. And then it becomes positive. In the direction of Q axis, it then becomes positive. So that means here it is most negative and then it becomes less negative, it becomes 0. It becomes less and less negative, it becomes 0 somewhere there, उसके बाद ये positive हो जाती है, उसके बाद ये Q axis, psi Q positive हो जाता है. This is when active vector 1 is applied. Okay, and this active vector 1 ends at this time. What is this time? This time is Tz. Say for example, ये time interval आपका यहाँ से यहाँ तक, this is Tz by 2. This time interval here to here is T1. Okay, after that you apply active vector 2. You can see when you apply active vector 2, इसका component along Q axis constant है, ये constant रहता है. So it will remain constant when active vector 2 is applied. We are finding its Q component. Q इस तरह है, so it is constant. And then we apply active vector 7. You can see active vector 7 जब हम apply करते हैं, आपका flux error vector इस direction में जाता है और ये origin पे फिर से 0 पे आता है. So it comes back when active vector 7 is applied. So this time interval when active vector 2 is applied, it is T2, and when active vector 7 is applied, this is again Tz by 2. That's it. So ये आपका this is the Q component of flux, stator flux error vector. This is how it changes. With null vector, it becomes negative. At the end of null vector, at the end of Tz by 2, it is most negative. When active vector 1 is applied, it first becomes 0, then positive. And at the end of time interval T1, then active vector 2 is applied. When 2 is applied, it remains constant. And then at the end of T2 time interval, null vector 7 is applied, it goes back to origin. It starts from 0, it ends at 0. This is how the Q component of stator error flux vector varies when switching sequence 0, 1, 2, 7 is applied in a subcycle. This total time interval here to here is subcycle Ts, which is Tz by 2 plus Tz by 2 plus T1, Tz by 2 plus T1 plus T2, and then plus Tz by 2 again. 0, 1, 2, 7 is the switching sequence. This is 7 here. This is Q component. What about its D component? D component मुझे नीचे, I don't have space, so I will take it down. I will show now its D component. Psi D tilde. That is stator flux error vector D component. Psi D tilde. अब आप देख सकते हैं ये D component है. This is D component. When null vector 0 is applied, आपका stator error flux vector इस direction में घूमता है. It moves along this. And since D is at 90 degrees with respect to this, so it does not have any D component. That means in this dz by 2 time interval, it does not have any D component. So it is 0. So that means here during this period, 0 vector is applied, null vector. When null vector is applied, your stator flux error vector moves in this direction. Its D component is 0. You can very clearly see because D is at 90 degrees with respect to this. And when error vector 7 is applied, okay, now let us see when error vector 1 is applied. So when error vector 1 is applied, so this is your d-axis. So d-axis, along d-axis, it increases. So it increases. So this is when active vector 1 is applied. This is when active vector 1 is applied. I will write here. And then when active vector 2 is applied, ये आपकी d-axis है. When 2 is applied, it comes down. ये देखिए, along d-axis, this is the maximum value, and along d-axis when 2 is applied, it goes back to 0. Okay, this is when active vector 2 is applied. उसके बाद null vector 7 फिर से apply करते हैं. When null vector 7 is applied, your stator flux error vector moves in this direction. इसका d component फिर से 0 बन जाता है. So it has again 0 component. Here null vector 7 is applied. So null vector 0 is applied, which is 0. Null vector 7 is applied, which is again 0. Then active vector 1 is applied, its D component increases. Then active vector 2 is applied, its D component decreases. So this is psi D tilde. Okay. Now our job is done, almost done. When we find Q and D components of stator flux error vectors, now our job is to find, our job is now to find the RMS value of current. For example, this is your, ID tilde. So you want to find D component of RMS value of current ripple. Now current ripple is I. Okay. And it has two components. It has two components, ID and IQ. If you want to find out, for example, its D component, you want to find RMS value of current ripple, D component current ripple, ID. How can you find D component of current ripple? I have told you, you have to find area under this. Okay. First of all, if this is your, line, a linearly increasing line, आप इसका square जब लेंगे, when you square it, it will become parabola like this. Similarly, this linear line, when you square it, square will become parabola, so like this. Okay. So if you have y equal to x square, y equal to x square will be something like this. It will be a line like this. This is x, this is x square. This is y equal to x square. Okay. Now after this, you find area under this. ये जो आपने psi d square, you have found square of it. Actually, you have to find RMS value. RMS value means square root of mean of square. Okay, that means ये जो है, ये पहले आपको square करनी है. This is line, for example, x. Its square is x square. So वो parabola बन जाता है. Similarly, when you have another linear line, its square is y equal to x square, and it also becomes parabola like this. Right? Once you have found parabola, then RMS value कैसे आप निकालेंगे? Area under these curves. For example, this is area. You try to find area under this curve. When you find area under this curve, how do you find area under this curve? That's very simple. You use this property of what we call as parabolas. ये आप rectangle, इसको rectangle 1 कॉल कर लीजिए, और इस साइड में आपका दूसरा एरिया है, ये दूसरी लाइन है y equal to x square, और इसका एरिया अगर आपको निकालना है, that will give you RMS value of the stator flux. So आप ये, you just complete this rectangle. So now we have two rectangles. This is one rectangle, rectangle 1. This is another rectangle, rectangle 2. And there is one property of these parabolas. One of the property of parabola is that the area under a parabola is 1/3 of area under the rectangle. That means अगर आपकी equation है y equal to x square is your parabola, and when you plot it, this is x, this is x square. Okay, तो equation ये बन जाती है, ये ग्राफ बन जाता है, वो ये rectangle आपका है. What is the area of this rectangle? Is length into breadth. Length इसकी है x और breadth है x square. So area of rectangle is x square into x, that's x cube. And what is area under this parabola? The property of parabola says, I don't know whether you have studied that or not. The property of parabola says that the area under the parabola is 1/3 of area under rectangle. What is area under rectangle? X cube. So it is x cube by 3. In a similar way, what you have done, first of all, you found d component of stator flux ripple like this. फिर चूंकि आपको RMS value of flux ripple निकालना है, RMS value में root means square, so you have to square first this. So when you square this line, it becomes parabola. When you square this also becomes parabola. उसके बाद RMS value निकालें. What does RMS value mean? RMS value means area under this parabola. So you have to now find area under this. If you are able to find area under this parabola, that will give you RMS value of side E. And similarly, area, if you find area under this parabola, that will give you RMS value. Then you add the two, that will give you total RMS value of side E. Side E का total RMS value आपको निकलेगा area under this parabola plus area under this parabola. And the property of parabola says that the area under parabola is equal to 1/3 of area under rectangle. और आपके पास दो rectangles है, ये एक rectangle है, ये दूसरी rectangle है. So area under this parabola will be 1/3 of area under this rectangle, and area of this parabola will be 1/3 area of this rectangle 2. Okay, so ये area, this will be 1/3 into area of rectangle 1, और इसका area, ये जो area है, area will be 1/3 in area of rectangle 2. So therefore, if you know the dimensions of these rectangles, find area of rectangle. Okay, divide that by 3, that will give you area under this parabola. Similarly, you know the dimensions of this rectangle. Find length and breadth, find area of this rectangle, divide that by 3, that will give you area of this parabola. Add up the two, that will give you total area of this curve. And total area is nothing but RMS value of your flux, D component of the stator flux ripple. So therefore, D component of stator flux ripple, you can find its RMS value like this by finding RMS value of this parabola and RMS value of this parabola by the same method which I have just now discussed. Now when I find D component of stator current ripple, similarly I can find Q component of stator current ripple, RMS value, using same techniques as this. I know D component, I know Q component. RMS value of stator flux ripple along D component, RMS value of stator current ripple vector along Q component. Once I know by finding areas like this in this curve as well as in this curve using the same technique which I have just now discussed, then what you do, you transform dq back to alpha beta. Since you have transformed alpha beta to dq, reverse transformation is also possible. So next step is reverse transformation. Reverse transformation from synchronously rotating dq reference frame to stationary reference frame alpha beta. उसके बाद another transformation you do from alpha beta to ABC. Transformation from alpha beta stationary reference frame to ABC stationary reference frame. So it is very simple. So what you have to do, you know now what is your psi d RMS, RMS value of stator flux current ripple. along d-axis. You also know what is the RMS value of stator flux vector, stator flux ripple vector along q-axis. You transform them into alpha and beta. That will give you psi alpha RMS and psi beta RMS using reverse transformation. Transform alpha beta back to ABC, because if you remember when we started our discussions on space vector PW, we transformed from ABC to alpha beta. The reverse transformation is also possible. If you have transformed from ABC to alpha beta, you can transform back from alpha beta to ABC. When you transform it back to ABC, you will find psi A RMS, psi B RMS, and psi C RMS. That is stator flux ripple vectors A, B, C. And I have already told you that current ripple, stator flux is directly proportional to current. So this psi A will give you IA ripple, RMS value of phase A current ripple. Psi B will basically represent RMS value of phase current B ripple, and psi C will represent RMS value of phase current C ripple. So therefore you will be able to find a current ripple in the currents, phase current IA, IB, IC, because psi A, psi B, psi C are directly proportional to this IA, IB, IC. That's how you can do it. So this is how we can find, current ripple in all the three phases. So what you do, you first transform alpha beta to DQ, find stator flux ripple, when different voltage vectors are applied, find stator flux ripple vectors, D component and Q component. And then, integrate the stator. First of all, you have to find error voltage vectors. Find, when you transform from alpha beta to DQ reference frame, find error voltage vectors when different vectors are applied. For example, when null vector 0 is applied, when null active vector 1 is applied, when active vector 2 is applied, find error voltage vectors. And I have shown you that process, how to find error voltage vector. Once you know the error voltage vectors, integrate them. That will give you, stator flux error vector. And just few moments back, we have drawn that stator flux vector, ripple vector, that was something like this: 0, 1, 2, and 7. Okay, and then resolve it into D and Q components. When you resolve it into Q component, stator flux ripple vector psi Q is like this, and it is D component, psi D. Stator flux ripple vector or D component is like this. And then you have to find RMS value of this psi Q and psi D. And this is the procedure. For example, मैंने यहाँ psi D लिया, and you have to find RMS value of psi D. For this case, you first square these lines. Those will give you parabolas. Find area of this rectangle. Find area of this rectangle. Area under this parabola is 1/3 of area of this rectangle 1. Area of this parabola is 1/3 of area of this rectangle. So that will give you total area of this parabola, and that will give you RMS value of psi D RMS. Similarly, you can find psi Q RMS. Once you know psi D RMS, you know psi Q RMS, transform that first into alpha beta and from alpha beta to ABC. So that will give you psi A RMS, psi B RMS, psi C RMS. Psi A RMS will be nothing but IA ripple current IA RMS, ripple in current IB RMS, and ripple current IC RMS. This is how you find the ripple currents in 3 line currents or 3 phase currents. This is the technique. Okay, so I will end my today's lecture here. This will be more clear to you in future lectures. In our next lecture, we will continue our discussions on how to find stator flux ripple vector, and consequently how to find the current ripples. So more on it in next lecture. Thank you.